Okay, so here's the last problem we almost finished. I didn't do the substitution, the arithmetic on the end. But as we finished, I said a couple times, if we integrate with respect to x, we got to think top and bottom. I said it a couple times, if we integrate with respect to x. And maybe some of you caught that, like, well, what's she talking about? We always use x, so why is she saying if we integrate with respect to x? Well, you don't have to integrate with respect to x. That's just what we did when we set up vertical rectangles. Vertical rectangles are always going to be associated with integrating with respect to x, because when we talk about that width, which is a small change in my x value, change in x, frequently we use the delta symbol to indicate change in. And so that width of that rectangle, change in x, delta x. And so we've been integrating with respect to x, but there was no, if you think about it in terms of area, whether my rectangle stands up vertical or lies on its side horizontal, area is still easy to get. It's still length times width. And so there will be times when it's convenient to integrate in terms of y. And that's what we're going to do. We're going to integrate in terms of y. Now, why would we do that? So again, the picture here, we had to do two integrals because top and bottom changed. So we didn't know about this possibility of integrating with y. And again, you still don't really know anything about it because I haven't explained it yet. So another way to view this picture, instead of filling it up to, think Riemann sums here, and to find the area, we're filling it up with vertical rectangles that get smaller and smaller, narrower and narrower and narrower until they're just line segments. So we're filling it up with vertical rectangles, smaller and smaller, smaller. Just the concept of area, we could have filled it up with horizontal rectangles and still got the area. So if you're finding area, filling it up with vertical rectangles or filling it up with horizontal rectangles, not going to make a difference on area. So let's think about the same problem, but think about it in a different way this time. Let's zoom in a little bit. Let's consider the same region. Notice the left side of the region is always the sideways parabola, and the right side is always the line. When it is the case, the right and left sides of the region remain unchanged throughout the interval being considered, it will be easier to integrate with respect to y and use horizontal rectangles. Because think about it. If I were to estimate this area by filling it with horizontal rectangles, or even when I do a Riemann sum and get the exact, limit of Riemann sum and get the exact area, it doesn't matter if I fill it with horizontal rectangles or fill it with vertical rectangles, I'm still going to come up with the area. And so it still would be the same thing. This time, that little width there I'm going to call delta y. And so the area of the rectangle, I don't really know why I'm using red, but I've gone with red, so let's go with red. The area of that rectangle, we'll call it length this time. I'm going to call it length. So length times width. And we just called the length, or the width, delta y. Now that length, let's call this curve over here f of y, and this curve over here g of y, x equal f of y, x equal g of y. That length there, the way I'm going to get a horizontal length, is right minus left. Now notice very importantly here, I went right minus left. The way you get a horizontal distance is right minus left. And then if I did a Riemann sum, you would have the integral in terms of y. And then I switch to dy. And so we can integrate with respect to y. Now, to get this guy set up in order to integrate with respect to y, to integrate with respect to y, we will need to solve each equation in terms of y. If you're going to integrate using y, your variables need to be in terms of y. So for y equals square root of x and y equal negative square root of x, solving for x we'll get, and we're able to do these guys at the same time because they're both essentially the square root of x. That if I'm solving for x, I would square both sides. And so I get y squared equals x, and doing the same thing over here, just being, I guess, extra specially, I can't finish that sentence, so I'm just going to stop trying to finish the sentence. Solving those first two equations so they're in terms of y, or in other words, we solve for x getting the epsilon, we get x equal y squared. Solving the next one in terms of y, that's going to give me y plus 2 equals x, where x equals y plus 2. Just like before, I'm going to need these points of intersection, A and B, but in terms of y. I'm going to need those points of intersection. So AB, the points of intersection of x equal y squared and x equal y plus 2, just like always when we're doing points of intersection, set the two functions equal to each other and solve. So it's y squared minus y minus 2 equals 0. That factors to y minus 2, y plus 1. And so we get y equal 2, y equal negative 1. Which should look reasonable from the graph. Can I get it all on one page here? There we can get, I'll zoom back in a moment. But it should look reasonable from the graph. Y equal 2 looks perfectly reasonable. Y equal 1 looks perfectly reasonable. Again, you're not allowed to guess by looking at a graph, but your graph should confirm what you found algebraically. So we're starting to get this set up in order to use y. That I have now the left and right sides. The right side is the line, which is now y plus 2. The left is the sideways parabola y squared. Then I have my points of intersection. So the graph looks like this, where the sideways parabola is that y squared minus 1. And what about green? Let's use, how about yellow? And that diagonal line is x equals y plus 2. And then I very concretely found that that point there was y equals negative 1. And notice it's along the y-axis. And I very concretely found there that that point B was y equal 2. And so I'm now ready to integrate with respect to y, thinking about horizontal rectangles. And so then it says in words there, the area can now be found using horizontal rectangles and integrating with respect to y. When given a region whose left and right sides are consistent, or when we're given functions in terms of y, it will be easier to use horizontal rectangles and integrate with respect to y. When we do this, we will say that the area equals the integral from a to b, right curve minus left curve, where c and d are the y coordinates of the lowest and highest points on the region. And so in this particular case, yes, we did it with x. And we could have gotten that answer. I just got bored, so I didn't work it all the way out. But we could have gotten the answer. It was just arithmetic after that. But I can get the same answer by using y. So in this case, my area is going to be the integral from C to D, right minus left, dy. My low point, and I guess I should have called those C and D instead of A and B, but oh well, I didn't. My lowest point was y equal -1. My highest point was y equal 2. Then right minus left, y plus 2 minus y squared dy. And that's going to do it for us. It's going to do it in one integral because right and left are consistent, and so I can just fill it up with horizontal rectangles. Because remember, all the integral is doing here is it's finding every single possible rectangle. As those rectangles get smaller and smaller and smaller and smaller, or narrower and narrower and narrower and narrower until they're line segments, and then just adds them all up. That's what the integral is doing there. And so that is the length of every one of those rectangles in there is given by that. There's my length, there's my length, there's my width. It's adding up the areas of all those rectangles and giving me that total area. But here, since there's one sort of representative rectangle, I can do it with one integral. As opposed to when I did it for x, there were kind of two representative integrals that did it. That when I did x and vertical rectangles, there really were two types of rectangles, so I needed two integrals. But when I use y and horizontal rectangles, I only need one. Then finishing this out, integrating, that's going to be 1/2 y squared plus 2y minus 1/3 y cubed. Evaluated from -1 to 2. Remember this part right here checks by differentiation. And when you're doing these problems on your own, you should, especially on these easier ones, you can differentiate that in your head. Check it. Then doing the evaluation, and this is the last step I'm going to do because I'm going to get bored after this. Plug in the upper limit, plug in the lower limit, and subtract. I prefer to work term by term. So 2 minus -1 minus 1/3 2 cubed minus -1 cubed. And it's just arithmetic after that, which I will leave you guys to do. But I will say, I know a lot of you are going to use your calculator for your arithmetic. And I said this once fleetingly before, but I'll say it again. If you're doing your arithmetic with your calculator and you go to square the number -1, it has to be in parentheses. If you don't put the negative number in parentheses, you aren't squaring the number -1. You're taking the opposite of 1 squared, which is different than squaring -1. So if you're using your calculator, be sure you put negative numbers in parentheses when you raise them to an exponent. Otherwise, you're not going to get the answer you expect. And so the point to this video, and we're going to do one more video after this, that because my left and right sides were consistent, this guy was easier to do in terms of y. When we go and do the next guy, it also will be easier to do in terms of y. So one more video after this, and then my lectures in Calculus 1 are done.